This video was sponsored by Brilliant. One of the most common video requests I get is to explain why low-level projects are full of these strange operators and hex numbers. Today, we're going to break down the basics of Bitwise Operations and learn how to manipulate individual bits, even though computers naturally force you to work with bytes as a unit. Hi friends, my name is George, and this is CodeCrafters. What's happening here is actually very simple to understand. In fact, you can do exactly the same in high-level languages like JavaScript. You just rarely ever need to. Before continuing with the main topic, there's something important we need to understand. At the bare metal level, everything has to be implemented with physical connections. Because of that, CPUs are designed to operate on a specific number of bits at once. A 16-bit processor, for instance, is designed to perform operations on 16-bit chunks of data. If we want to add two 24-bit numbers, that CPU cannot perform the operation in a single step. It needs to split the work into two steps. On the other hand, if we need to add two 8-bit numbers, there's no need for special 8-bit circuitry. The CPU can simply use its 16-bit adder and fill the unused inputs with zeros. The number of bits a CPU is designed to work with at once is what we call a word. In computing, a word is the processor's natural unit of data, a fixed-size chunk that the instruction set and hardware are optimized to handle as a single unit. This is the main reason why essentially no computer can manipulate individual bits using regular arithmetic operations. There's simply no dedicated circuitry designed to operate on single bits that way. When we write code, we constantly perform operations like addition, subtraction, multiplication, and comparisons to make decisions. For educational purposes, let's call these regular operations. Regular operations work on an entire word at once. The result depends on the numeric value of the whole word, not the value of each bit individually. If that sounds confusing, here's an example. When adding two 16-bit numbers, the value of, say, the 8th bit in the result does not depend only on the 8th bits of the inputs. 0 plus 0 is obviously 0, but the result also depends on everything happening to the right of that bit, because any carry generated by the lower bits will propagate upward. A bitwise operation, on the other hand, still works on a word, but it processes each bit independently of the others. Suppose we have the numbers 14 and 4, each represented as 8-bit words, and we're performing the bitwise AND operation between them. A bitwise AND tells the CPU to perform a logical AND on every pair of bits in the same position in both operands. Just like we explained earlier, the operation still runs over the entire word. The CPU reads and processes the whole 8-bit chunk at once. But here's the key difference. The result of each bit in the output depends only on the two bits in that exact position from the input words. Nothing else. There's no carry, no borrowing, no influence from neighboring bits. That's what makes bitwise operations fundamentally different from regular arithmetic operations. Even though the CPU processes the entire word at once, each bit in the result is computed independently, based solely on the corresponding bits in the input words. Nothing else. There are 6 main bitwise operations, and their names are very descriptive. They operate over an entire word, but their logic is applied at the individual bit level, not at the group level. A bitwise AND performs the logical AND operation on each pair of corresponding bits in two values. A bitwise OR performs the logical OR operation on each pair of corresponding bits. A bitwise XOR performs the logical exclusive OR operation on each pair of corresponding bits. And the bitwise NOT applies the logical NOT operation to every bit in a single value, essentially inverting each bit inside that word. Additionally, there's a subset of bitwise operations known as bit shift operations. Like the bitwise NOT, these operate on a single word. All they do is shift every bit inside that word either to the left or to the right. When you shift a word, one bit gets pushed out, and a new bit has to appear on the opposite side. That incoming bit can be determined in a few different ways. Fill with zeros, fill with ones, or reuse the bit that was pushed out on the other end, a rotational shift. And believe it or not, that's all these operations really do. All programming languages provide their own syntax to perform these operations. The question now is, Why do we even need these operations in the first place? Well, because they open the door to all kinds of clever tricks that are incredibly useful in certain situations. Useful like today's sponsor, Brilliant. If you're the kind of person who enjoys peeling back the layers of how computers actually work, Brilliant is hands down one of the best ways to push your learning deeper. Brilliant is built around a simple idea. You learn best by solving problems, not by watching someone else solve them. And when you experience that kind of active problem solving, you start to feel something shift. Concepts that used to feel abstract suddenly become intuitive. You start thinking more clearly, more logically, more like an engineer. What I love about Brilliant is how it meets you exactly where you are. It figures out your level, adapts your practice, and helps you progress at your own ideal pace, without ever talking down to you. It assumes you can do this stuff, and then proves it to you. Since we're talking about bits and low-level operations today, the course I recommend checking out is Digital Circuits. It shows you how computation is built from the ground up, with logic gates, state, binary operations, the real machinery behind everything we just explored. And Brilliant guides you to those aha moments where everything clicks. To start learning for free, go to brilliant.org/coredumped, or scan the QR code on screen or click on the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. And now, back to the video. Imagine you're working on an app with millions of users, and you're assigned a simple job. Implement a settings screen like this one, full of toggle switches, but do it in the most efficient way possible. Toggle switches map naturally to Boolean values, since each switch represents a state, enabled or disabled. So the obvious way to store them is with true and false. If you think about it, in binary, all we need to represent a Boolean is 1 bit, because a single bit can hold exactly 2 states, 1 or 0. The problem is that memory and storage hardware don't work at the bit level. Their smallest addressable unit is 1 byte, which is a group of 8 bits. When the CPU fetches or stores data, it must provide a memory address, and that address always refers to a full byte. There is no instruction to read bit 3 or write to bit 5 directly. Memory operations always work on the whole byte. Because of this, programming languages define their basic data types with a minimum size of 1 byte. So when we declare a Boolean variable, it will normally be stored as a whole byte, even though only 1 bit is actually used. The remaining 7 bits are wasted. If we need to implement 8 toggle switches and store their values, we would normally need 8 bytes of storage, even though the toggle states themselves only require 8 bits. This might not seem like a big deal. In this example, we're wasting 56 bits, or 7 bytes, practically nothing compared to gigabytes of RAM or terabytes of storage. But across 50 million users, that tiny waste adds up to more than 350 megabytes of extra storage, space that isn't actually being used for anything. And you might think that still doesn't sound like much. But remember, this is just one screen. Imagine how many other configuration menus with toggle switches this app might have. And if you still don't see the importance of this, I'll get to another example later in the video. For now, as a good engineer, you're assigned the task of solving this problem. Instead of storing each toggle as a full Boolean, you decide to pack all 8 toggle states into a single byte using 1 bit per switch. This is where Bitwise Operations become incredibly useful. To make this easier to follow, let's define 4 higher-level operations: set, clear, toggle, and read. All of them receive a word and a number n. And just to be clear, inside a word, bit indexing always starts at 0, meaning the least significant bit is bit 0 and the most significant bit is bit 7. So if n equals 3, that means the 4th bit. Set selects the bit in the position n and sets its value to 1. Clear selects the bit in the position n and sets its value to 0. Toggle selects the bit in the position n and flips it from 0 to 1 or 1 to 0. And read selects the bit in the position n and returns its value as a number, so it returns 0 or 1 as an integer. Here's how we can set the value of a single bit inside a byte. As we mentioned earlier, there's no straightforward way to directly modify a single bit inside a word. So if we want to set, for example, the bit in position n equals 3 to 1, we need to operate on the entire word in such a way that all the other bits remain unchanged, and only the bit we care about becomes 1. So how do we do that? If we look at the truth table for the logical OR operation, we can see that whenever either input is 1, the output is 1. So the trick is this. We create a second word that contains all zeros except for a 1 at position n, and then we apply a bitwise OR between our original word and this new value. This extra value is called a mask. No matter what the original value of bit n was, the result will have a 1 in that position, because the mask contains a 1 there. All the other bits stay exactly the same. 0 or 0 is 0, and 1 or 0 is 1. And voila, we've set a single bit inside a word without altering any of the others. Now notice that we need a different mask for each bit position. That would be tedious to type manually. So to generalize the process, here's what we do. We start with the number 1, binary 000000001, and shift it to the left n times. So, for example, if we want a mask for the bit in position n equals 4, we shift left 4 times, and that's our mask. So, in general, to set a bit, we left shift the number 1 n positions, and then OR that mask with the original value, and that's the implementation of the set function. The clear function follows a similar idea. Since we can't modify a single bit directly, we need a mask that forces bit n to become 0, while leaving all the other bits untouched. The logical AND operation is perfect for this, because its output is 0 whenever either input is 0. So if we want to clear bit n equals 1, our mask needs to have a 0 in that position, and 1s everywhere else. After applying bitwise AND between our word and this mask, the 0 in the mask forces the output bit at that position to become 0. Since all the other bits in the mask are 1, none of the remaining bits change. 0 and anything is 0, and 1 and 1 is 1. To create this mask generically, we start with the number 1, shift it left to the desired bit position, and then apply a bitwise NOT, inverting all the bits. And that gives us the implementation of the clear function. Now for the toggle function, flipping a bit from 0 to 1 or from 1 to 0. Here, the exclusive OR operation is ideal. Usually, exclusive OR is explained as one or the other, but not both. But for our purpose, we can view it like this. When the second input bit is 1, the output is the first input flipped. When the second input bit is 0, the output is the first input unchanged. So the mask we need contains a 1 only at position n. That way, the resulting bit at that position is flipped, while all other bits remain unchanged. So we start with the number 1, shift it left n positions, and once we have the mask, we XOR it with the original word. And that's how we toggle a single bit inside a word. Finally, the read function. Here, our goal is to extract the value of a single bit, either 0 or 1, and return it as an integer that can be used in normal operations. In this example, we read bit position 7, so we should return 1. If n were 6, we would return 0. If n were 4, we would return 1, and so on. So this function returns either 0 or 1. To do that, we need to put the value of our bit into the least significant bit of the output word. So the first step here is to right-shift the word by n positions. However, after shifting, the value might contain other bits equals 1 to the left, making the return value different than 1 and 0. We need to get rid of those bits, so we apply a bitwise AND using the number 1 as mask. Since AND outputs 0 when either input is 0, all bits except the least significant one are cleared, and the bit we care about remains unchanged. So to read a bit, right-shift the word n positions, and the result with the mask 1, and that gives us the bit value as a normal integer. And these 4 basic functions are all we need to read and write to a single bit inside a word. This technique of storing multiple values inside a single byte is called bit packing, and that's how we solve the problem we described earlier. As I mentioned before, this might seem a little exaggerated. In most situations, You should just use the data types provided by your programming language and only dive into bit packing when you truly need to. This approach becomes necessary mainly when memory or storage is extremely limited. For example, in the world of embedded systems. Imagine you're working with a sensor that reports 4 possible moisture levels every second, and you're asked to program a microcontroller to record those readings continuously for 1 full year. But the available onboard storage is tiny, only 10 megabytes. Since 4 possible states can be represented with just 2 bits, a single byte is more than enough to store 1 reading. But if you run the numbers, you'll quickly discover that even storing 1 byte per reading is too much. Those 10 megabytes simply won't last an entire year. This is where the ability to work with individual bits becomes invaluable. By packing 4 readings into a single byte, you reduce the storage cost by a factor of 4. And if you do the math again, you'll see that with this approach, those 10 megabytes are suddenly more than enough to hold a full year of data. Back in the 80s, when memory was limited to just a few kilobytes, this technique of splitting a byte to store multiple values was extremely common. The NES, for example, had only 2 kilobytes of RAM. In the original Super Mario Bros., almost everything was bit-packed. A single bit was used to track things like whether Mario is small or big, whether he has the fire flower, whether he's invincible from a star, his facing direction, or whether he's in the ground or in the air. Now, you might think this isn't really a problem anymore in general-purpose computing, since having gigabytes of memory and terabytes of storage is pretty much standard in our days. But the truth is, bitwise operations still play a huge role behind the scenes. The same encoding and compression algorithms that allow your videos to occupy just a few megabytes instead of multiple gigabytes rely heavily on bitwise operations. And beyond storage, bitwise operations are absolutely essential in other areas of computer science, especially encryption and hashing, both of which are fundamental to modern cybersecurity. As I mentioned in a previous video, if you explore the code of any open-source cryptography library, you'll find bitwise operations everywhere. Finally, keep in mind that the helper functions we defined earlier aren't really used that often in real-world code. Bitwise operators are usually used directly, the same way we just write the plus or minus symbol when doing addition or subtraction. For people who work at this level, bitwise operations are simply part of daily life. Of course, this also means that usually the masks are not generated dynamically. They're written directly into the code. And because writing long sequences of ones and zeros is extremely error-prone, low-level developers avoid binary entirely and write their masks in hexadecimal instead. So if you've ever looked at a low-level project and wondered why the code is full of weird hex numbers, now you know. If they're sitting next to bitwise operations, they're almost certainly masks. Hex numbers in programming definitely deserve their own video, so make sure you're subscribed because you won't want to miss that one. I'm going to go ahead and wrap things up for now. If you want to support the channel, please check out the sponsors in the description below. And if you enjoyed this video or learned something new, please hit the like button. It's free, and it helps me out a lot. See you in the next one.